represent Oxford Brookes University, United Kingdom. Of course, in represent Ukrainian University from Ternopil. Yes, Ternopil, West Ukrainian National University and Institute of Modeling, National Academy of Science in Ukraine. Cancer. Lina, a lot of time work in area artificial intelligence, in application AI for medicine, for other systems. It's our pleasure. We a lot of time participate and cooperate with Professor Inna Skar-Hambadurova and your team in a lot of European Union funded projects as Tempus, Erasmus Plus, and Horizon 2020. Officially, now represent Oxford Brookes University in United Kingdom. Inna, welcome for your presentation. Please, this place.
Thank you for the so warm introduction, and I'm so sorry for the delay today. There are some strikes, so thank you very much for your patience, and hope you will enjoy my presentation today. Before I start, first of all, I would like to say my highest appreciation for all of you who are present here and online and offline, of course, and our colleagues from Greece who organized this event, and of course my highest appreciation to my kind friend Vyacheslav Harchenko, who invited me here. So I have the opportunity to share our experience, some projects that we are engaged in and that we are actually working on them. So let's probably start. Yeah, F5. No? Oh, okay. Share screen.
Dear colleagues, do you hear us and do you see presentation?
Yes.
Everything's okay.
Okay, thank you. Welcome.
Okay, so the topic of my presentation will be about the mechanism of autonomous decision-making in self-governing robotic systems. So I'd like to share our experience with this really interesting area. And a little bit, of course, I will be talking about the security and artificial intelligence, mostly artificial intelligence, of course. So now I'm engaged in 3 different projects for many years already. The first one is artificial intelligence for healthcare. And in this particular area, I worked with Project Saras. Saras, this is it states from self-autonomous robotic assistant systems, which aims at developing of next generation surgical robotic system that will allow single surgeon to execute robotic minimally invasive surgery without need of experts assistant surgeons. So this is a pioneering idea which was partially realized during one of the European projects. And actually it was first step in one of the first step in development of such systems, and leads to different interesting results and application. And actually we also, so the part of this research lead us to two interesting directions. The first one is autonomous decision making, which we realized in different in different aspects, and I'm going to share with you today, and explainable AI. So explainable AI, one of the really interesting, tremendous areas that we also worked in the context of healthcare and in the context of robotic systems. So the second project is devoted to development of the unmanned ground vehicles, and at our university we have two different research labs, or even three very, very soon, which are worked with such systems. So the first one is robotic and AI. When we worked with Formula One students, and actually Oxford Brookes University was one of the leaders at in the UK who involved in development of unmanned vehicles. Actually our direction now is unmanned ground vehicles, which can be used for different aspects that we will discuss further. So in this context, today we will discuss a little bit global path planning algorithms, again some results and lessons learned. Some other directions which we are engaged right now is the temporal distributed attacks against video-based action recognition, which can be really, really important in terms of different unmanned ground and air vehicles as well. And the third direction, as I said, this is the exploring vulnerability and resilience of critical infrastructure in face of large-scale disruptions, which we are working with our Ukrainian partners and partners from other countries. So today I will stop on two interesting topics. The first one, autonomous decision-making and global path planning in the context of different aspects of artificial intelligence and security. So first of all, since we are talking about autonomy, we need to mention about what autonomy actually is. And the first thing that's normally autonomy is associated with some specific self-governing behavior. And it can vary from very simple things like partial or low autonomy systems, when we need or when we expect from robotic system just the mapping or localization, then move further into the task autonomy with, for example, autonomy or in terms of a surgical robotic system. It can be autonomous robotic anastomosis or some specific target decision systems, and then moving further to the full mission autonomy. When human actually act as a supervisor to the high-level peer-to-peer collaboration. And what is interesting here is that the top level of autonomy assumes full situation awareness, which is not reachable yet, but it also taken into account self-goal setting, which also not covered yet with our algorithms and artificial intelligence systems, and there are a really, really wide area for our research and also task realization. So for task realization, this is the area when robotic systems actually play a really important role, and they are really successful. What should be mentioned here is that the self-aware autonomous systems, they can work on, they can interact to some extent really efficiently with humans, and utilize some data that we programmed is there. But peer-to-peer collaboration or human-robot interaction may be much more difficult than realization than the full autonomy. And the core essence here is that the robot needs to understand what actually human expect from robotic system. So it should be more cognitive than physical. So physical, this is the essence that each robot normally have some specific functionality. What we are going to achieve is this natural understanding of the situation and collaboration in a human way with this robotic system. So in this context, our first case, of course, this is the SARAS. As I said, so experimental setup for SARAS consists of different connected systems. First of all, this is the artificial human abdomen and pelvic region model. So we worked solely on the human phantoms. This is not the real parts, of course. These phantoms was designed and produced by Austrian Center for Medical Innovation and Technology in collaboration with the MRI group at the University of Dundee and SARAS partners as well. Then it also include, and you can see here the part of the Da Vinci surgical system with 2 active robotic arms, which actively actually represent the interface between the lead surgeon and the patient. And SARAS multi-robot surgery systems, which was developed with 2 versions. In first version, it was fully teleoperated by the assistant surgeon, and the second system was fully autonomous. So we actually are interested in really autonomous system. And what is important here is this, the concept behind efficient autonomous decision-making and human-robot collaboration include at least 3 important elements. First of all is the gathering and understanding complex information from the environment. In this particular case, this is the surgical regions. The second one is recognizing teaming context and setting goal. So since we are going to make a robotic system that able to collaborate with a surgeon, it can work in or it can mimic at least some cognitive aspects of the natural collaboration between the 2 surgeons, like a main surgeon and assistant one, because our initial goal was to substitute a human on this robotic system. And then, of course, it needs to take specific proper actions following a high-level strategy. So we need to have these 3 aspects to realize the human-robot collaboration. What does it mean? Actually, it means that we need to have some sort of a cognitive architecture. Probably all of you already know that what we have to this moment, these absolutely fantastic ChatGPT systems that can analyze a huge or train a huge amount of data and mimic the human human interaction. So you can easily ask the question, or you can ask any question and receive really similar answer, similar to human contact, human conversation answer. So what? But if you ask directly, for example, ChatGPT, whether do you use any cognitive architecture, the answer will be no, because they use completely different set of algorithms. They are really efficient, they are amazing, and to this moment they can understand and analyze a lot of data related to the, not just the text data, they move to visual data as well. But still, cognitive architecture for systems who are fully autonomous should be the part or essential part of the of such systems. So for the SARAS autonomous decision making, on the beginning of the project, we developed such architecture which include a different different classifiers. So this architecture is really similar to the idea which is used to this moment in 90% of the self-driving cars. So we have a lot of different deep learning classifiers which combine together, and then we worked with these classifiers to generate, to fuse this data and generate meaningful decisions. So the same idea actually was in the beginning of the SARAS project. So we don't use the new approach, which is called end-to-end, when we have let's say some classifiers in the beginning, then one huge deep learning algorithm, very trained, and then we have some decision, because this is much, it needs much more energy, resources, training, and so on. So idea was to use classical approach. So in this classical approach, our cognitive architecture include visual content and audio content. So for visual content, since we are working with surgical area, we have several different classifiers. One of them performed face recognition. You can assume that each surgical procedure has or can be divided on the phases. So we have face recognition. Face recognition actually allows us to reduce the space of possible decision for SARAS, for robots. Then we had action recognition, then tool detection, tool tracking, scene understanding, which we call semantic segmentation module. Then also we had anomaly detection module, which realized based on the completely different architecture to understand what's unexpectedly can happen during our operation. And we have, as I said, a speech recognition model, so which should be like a second modality to this system. So the main task here was for SARAS was based on all of this observation. System should generate some specific decision about what to do, and what is really important, when to do. So specific action at the specific moment of time, based on analysis of all this current situation. So, and in this aspect, I would like to emphasize that in the beginning of the project, and this was actually our first lesson learned, we thought that since this is not really the situation in a surgical scene, does not change very quickly. So our first assumption was that it should be much easier that, let's say, a situation on the self-driving cars, because we already have the experience, we have special, we have our own data set, so we thought that it would be a little bit easier. But unfortunately, if you look at the real representation of the surgical scheme, the level of complexity for understanding what's going on and during the procedure is much more difficult, because the structure does not have specific forms. So deep learning algorithms are faced with a lot of challenges here. So we don't expect that we will achieve 99% of accuracy from the deep learning algorithm. And this was actually one of the main reasons of challenges that we faced during this project. But again, so we have action detection system, we had semantic segmentation system, which is based on the RES50 architecture, and then we also have the generative architecture for recognition of anomalies in this particular system. So what we generate at the end and how it can be represented is that we had a set of all available alternatives and decision strategies to task generation within which specific phase. So we track different objects with different deep learning algorithms. And then, as I said, for each specific phase, we have a very, very limited number of task alternatives which allowed to be permitted to this specific for our robotic systems. And so if you look on the left side, you probably can find them like in a very, very straightforward way. But actually what we have on each stage, this is the mix of different objects, different structures, and triggers. I will tell about them. Also, we have as I said, we have a speech which we received from a general surgeon. And based on this, we tried different strategy. Why we actually came up with different strategy, the main reason was our initial idea failed dramatically. And therefore, we tried different architectures, different strategies, and different approaches, which I actually want to tell you and share with you right now. So, according to our preliminary results, we defined that decision-making, and it's quite clear that all the data or all activity from a robotic system which help main surgeons should be very, very precise, because first of all, this is even if they worked with these phantoms, even though we need to train system in a such way that it can be useful at least for some specific actions. Otherwise, it makes no sense to work in this environment at all. Therefore, we tested different decision-making strategy. We started from classical final step machine, which we have general actions, face recognition, and speech recognition as the main input into the system. And then we applied different approaches, started with stating this face first of all, and then using different probabilities to achieve some results. Second approach was utility model. As you can see here, we used more sensory information, which also includes audio and visual context. And in this particular case, we used approach which is widely maybe used and suggested for gaming. So we use utility function and weighting model just to see whether it will work better or not. And then, and it was actually our initial idea to development of such system, it was trigger-based model. So we started from the idea, as I said, that two humans work in very close collaboration. And teaming actually means, especially surgical teams, means that assistant normally can predict for the actions from the main surgeon, and timing and the precise of the action that they provide is really crucial. So we thought that probably there are some signs from main surgeon, then we can catch up on our videos and then use these signs for development really successful model. We spent a lot of time to find these signs during surgical procedure. We found them, but I will stop a little bit more to explain what we have here. So triggered actions, face, anomaly, speech, scene, this whole information we use for our third model. And finally, we came up to the formal logic model. And this is like, the classical situation when we are building artificial intelligence. We tried all of the possible ways, and at the end, and the umbrella of AI, we have if-then system. So we also have this if-then system like a benchmark to check which one works actually better. So this is our first strategy. As you can see, we have FSM here, which utilize information from action detection and speech recognition module. And so it is based on the idea that, as I said, all our procedure divided on the phases. So on each phase, we actually trigger since we recognize specific phase, we have really clear algorithm what to do next. Switch to step 1, step 3, step 4, then again recognize phase and move between these phases. So this machine realized that transmission between states once the new action is recognized. It was not really successful, but to some extent, if we assume that surgeon never returned to previous stage, to some extent it can be acceptable theoretically, but practically there are a lot of challenges because this is the real world situation, and sometimes they need to return to the specific actions. Therefore, there's some sort of extension of FSM. It was this utility-based model when we have specific decisions and then their scores, like as I said in game and environment. Each action has specific weight, plus and minus, and based on this, on the combination of these score, this system able to make a decision. But again, since this is just an extension, it means that we cannot return to the previous phase, and it was the main limitation for this model. Therefore, trigger-based model, our initial and the most basic idea, was realized, you can see here the 4 different classifiers: object detection, action recognition, phase recognition. Then also we have the anomaly detection. Anomaly detection, as I said, was realized using different architecture, and therefore it was this information about the anomalies was just used on the fusion stage, and then separate classifier which recognize speech, which we achieved from the main subject. So on the decision level, all data were used twice. So on the decision level, from the basic classifiers, because they represent the whole picture, and then they all was combined together using belief functions. But so this is the main representation or the main idea behind the triggering events. So system just, or Sarah just played for action triggers. So if we find some specific action like shaking or pointing on this specific area with instruments and recognize this, then Sarah's just like using the feedback to perform specific action. So let's say if surgeon made a circle or specific shaking, then you move in specific directions. This is the general architecture of this system based on the triggers, and here you can say how the local decision can be generated. So as you can see here, they started and they based on the recognition of actions, and this was the main drawback of this system. Because what we found after trainings, lots of trainings, because we did our specific data set, is that the triggering events, comparing to all the events that normally persist in this or exist on this system, are very, very rare. The most, let's say, if surgical procedure can be long, 45 minutes long, or we can detect triggers only 3-5 minutes. So these triggers is definitely not enough to train a system that can recognize them. So we need to have maybe a specific environment to do something else. So we need to extend maybe videos and improve our recognition accuracy. And our main idea was, of course, to improve size of surgical training data set to have the better decisions. And after After understanding this limitation, we came up with several possible decisions. The first one, of course, the data augmentation, and this is really good approach when you work with artificial intelligence, with data for machine learning. So actually there are two different directions. First one, increase your data set, and the second one is to work with your model, change model, their architecture, maybe training time, and so on. So higher parameters. But one of the research that they reached 94% of accuracy after data augmentation, so we focus on this direction. So our team was divided into two parts, one work in a classical manner, one work on the increasing data set, another work on the improving deep learning algorithms. Then we also thought about the gesture standardization. So not just because actually it was 5 videos and 3 different surgeons filmed during this procedure, but style is completely different, phases, everything is different. So standardization could be potentially the solution for this one. But then we have the conversational protocol, and again standardization, the voice or commands for all the surgeons. Unsupervised, semi-supervised approaches also were tested, and then the good idea was to use 3D trackers and kinematics data. We did not do this due to limited time there for this project, and our final decision was combination of trigger-based and general activity model. So what we actually did. Our initial model, as I said, was based on the trigger, and in case if we find or if we are able to detect triggers, then according to our scheme, everything worked really good because specific trigger determines specific action, and trigger-based model in this particular case can generate some decision. But we also found that not just the triggers was the problem with in these systems. Action recognition, due to complexity of the environment, was also there, very, very challenging. But we found out that semantic segmentation model or recognition cell elements works pretty good. So we decided to switch or to combine two different ideas together and to base our second part on the semantic segmentation model. In this particular case, we recognize surgical instrument and organ or region. So organs or regions, they are changed to specific to some extent. So sorry, I need some water. And these changes allows us to make the model. And what results we actually achieved from this last model and from this combination? We had 3 videos or 3 different sessions from different phases. And in our first case, we explore the possibility of surgeon non-verbal collaboration. What does it mean? We simply switch off all of the voice recognition just to think or just to see whether our system can recognize something in this, just from semantic segmentation module with help some additional modules. And what you can see here is that the blue color is the decision-making output, and green color, this is the speech recognition module, which we don't use during training process. We just use it for testing, because this is what we actually what we have from the surgeon part, and this was his great intent, main intention. So mostly it works pretty good, but to some areas we receive really huge errors. And this is actually where our explainable AI or explainability enter into the game. And so, as you can see here, for some specification, from 11 minutes, we have the command from the surgeon like the full prostate, but instead our decision-making module generates the grafted catheter action. So what we did, we start to think what to do, and we make some sort of a barcode to have a look what the results from the classifiers we achieved. So we analyzed the results from all our classifiers, and we found out that starting from minute 11, one of our classifiers, this is the semantic segmentation, generates that the system recognizes catheter. So it's wrongly recognized catheter, and therefore this wrong recognition leads to the wrong command from decision-making module. What is interesting here is that as a human being, we are absolutely fantastic in recognition objects. So we believe to our eyes. But this system is also based on the same assumption. It believes to the results from visual recognition module. And since it believes to visual recognition module, if error appears in this module, it also transferred to the decision-making module. This is the main the results here. So for case 2, we check the efficiency of our autonomous decision-making in presence of both verbal and non-verbal command. So in this particular case, we use speech recognition module. And as you can see, we still have some errors, but speech recognition or adding additional modality significantly improve their results. So this combination of fusion of different modality on such type of system brings really good results. What we learned actually, first of all, we tested different decision-making strategies separately to choose the best one. Our results show that quality of recognition is one crucial component for establishing efficient decision-making policy. All perceptual elements drive efficiently in the decision-making process. Then we need to take into account the current level of recognition, because if we are working with self-driving cars or robotic systems, to provide the highest level of safety, first of all, system should generate really high level of accuracy. Moreover, even if you achieve 96 or 97% of accuracy, there is still 3% of errors, and it means that you definitely need to make some sort of a backward analysis and also involve explainable artificial intelligence to be sure that your model recognize right things, that data set is big enough and it provides you, and this is not the systematic error. This is really important. Then to reduce uncertainty for the robotic assistive action, following modification can be done. First of all, the large data set, we need a sufficient number of videos containing visual triggers in this particular case if you want to have this one. Then, as I said, explainability should be the part of the process. Fourth thing, and this is really important, we don't stop on this. We need to think about real cognitive architecture and introducing them into this system. But again, first thing first, first we need to have the good recognition rate, and the measure and reinforce the key decision generated by the robotic system also should be one of the direction here. So I believe that when we can overcome these issues or these challenges, we really can reach the human level or close to human level reliability in the decision making. So I very quickly, if you allow me, just move very shortly through our second case. It was the teledoc. This is the system which we realized for finding the pathway during the warfare scenarios. So again, when we are dealing with self-driving cars, but a self-driving robotic system that deliver some goods from point A to point B. To the specific of this task, as I said, when we have some unexpected events, we cannot use classical algorithms due to some circumstances related to the replanning. So what we have done so far, you can read our paper. This is the first step. I will not stop because lack of time, just very quickly. So our goal in this direction was the development and practical implementation rerouting global path planning algorithm, and we started from the this delivering. So from the Bresenham-based global path algorithm on grid maps. So why we use Bresenham for this particular cases? Because during the warfare scenarios, we are not really interested on the closest path, but we are interested on the safest path. And moreover, when we have some events that should be avoided, so our main goal to deliver food, maybe some medicine, using this unmanned car in safe way, in such way that it should be safely deliver all of this good. Therefore, we did some specific work. We started from Bresenham-based global path planning. Then we also moved to the we used several SOM architectures for this as well, which allows us to improve this algorithm. And finally, we delivered the global path replanning algorithm for emergency response on battlefield by using Internet of Battlefield awareness, situation awareness data. So yeah, I think you can read our paper. If you have this question, I'm more than happy to answer on the improvements that have been made. The first one is using this Bresenham line algorithm, of course, because in normal scenario they don't use, but as I said, they can allow to move near the walls or near the buildings. The second improvement was that we use state machine, which reduce number of cycles as well. And finally, when we faced with a problem of time or calculation time, we suggested this work as well, the approach when algorithm automatically can choose the direction and it significantly improve the results. So this is probably all from my side. If you have questions, no, not all, just the final point. And I like this slide too much, so I can't stop. Sorry for the delay again. So you probably know that the sayings, but just to say it again, the factory of the future will have only 2 employees, a man and dog. The man will be there to feed the dog, and dog will be there to keep the man from touching equipment. So in spite of this saying, I would say that we are on the beginning of this, on this really amazing and really interesting way. So we have a lot of challenges, ethical, technical, and many other issues that we need to to face, and we need to improve. But even though, if you're interested in this direction, that I'm more than happy to collaborate in this or any other direction. So please let's be in contact. Thank you very much.
Thank you very much. Dear colleagues, we work in offline and online modes. Hence, we can ask a few questions, but not a lot because we have not a lot of time. Welcome. A few questions. I check online, maybe.
No questions online.
No, I have questions as usually.
Welcome, Professor Shmylov.
Yeah.
But I asked you about very short formulation of question.
Short. This is an interesting decision-making strategy for unmanned moving vehicles. But do you have decision-making models in emergency? If we have moving vehicle, it will be emergency too. This is a weak models or new models.
Please,
models in emergency.
Please once more repeat your question.
No, if we have moving, maybe emergency.
Yeah.
Do you have models decision making in emergency? If this is the same models or new models?
Yeah, this is completely new model. Thank you very much for this question. Yeah, if you are talking about the second model, that this is definitely the new one. Because it takes into account several new, so this is the combination, of course, with some existing models. Yeah, but if we're talking about involving SOM, that to this moment, our experiments demonstrate that, unfortunately, the current level of technology does not allow us to use SOM, but in the future, it's definitely one of the best approaches. So I think...
Understood. Very interesting approach. Very interesting.
Thank you.
Thank you. Any other questions?
Thank you.
Okay, let's thanks once more Professor Inna Skar-Khabadurov. Thank you very much.